And we reach our last problem on the 6C8 assignment, and this is the amide ion NH2 minus. This one has a charge to it. It is minus. Sometimes it's good practice when you have a charge to it to just come straight over on your answer key. This one's ionic. The strongest intermolecular force it would have would be ionic. Sometimes it's smart to go ahead, circle that right out of the gate. They're still going to want to know the shape. But the fact that it's ionic, if the purpose of finding the shape is to determine what the strongest intermolecular force is, how strongly it can pull on other molecules, this one's minus. It is a full charge. That is about as strong as you can pull. So we'll go ahead and circle that right now. Ionic. Now that we have the ionic circled, we can come straight back over here and start working on its shape. There is one nitrogen from family Roman 5. That's 5 electrons. There's 2 hydrogens in Roman 1. 2 times 1 is 2 electrons. We have 7 electrons. But this molecule is minus, which means there's going to be 1 extra negative electron on here than we would normally expect to find. 7 plus 1, we have 8 electrons to work with. Who's in the middle? Can't be hydrogen. Hydrogen can only form 1 bond. The nitrogen needs 3 bonds with its 5 electrons to get a total of 8. So nitrogen will be in the middle, and we will surround it with 8. So we have our nitrogen right here. It is now surrounded with 8. I like to put my brackets up right away with the minus sign out here because this was NH2 minus, and I don't want to forget to do that. Wherever there's a pair of electrons, we can attach a hydrogen. So we can attach a hydrogen there. Maybe we can attach a hydrogen right here on this pair. We have our 8 electrons. Nitrogen has the 8 it needs, satisfying the octet rule. The hydrogens have the pair they need, satisfying the duet rule. So we don't need to erase or add electrons. In fact, we are ready to take it straight to a Lewis structure by replacing the shared pairs with a line. So we have our structure right here. This is our Lewis structure. Now it's time to figure out what the shape is. We already know it's ionic, so that's going to be the strongest intermolecular force. But let's find out what the shape is. And we need to count the total things surrounding the central atom. The total things would include the number of bonded atoms. There's 1 hydrogen, there's 1 hydrogen. We don't count bonds, we count atoms. There's an atom, there's an atom. And then we count pairs of electrons. So we have 2 hydrogen atoms, that's 2. A pair of electrons here is 3. A pair of electrons there would count as the 4th thing surrounding the atom. There's 4 things surrounding this atom right here. So right here, our steric number is the total things surrounding the central atom. We have 4 things surrounding the central atom. We now know what family it would belong to, because anything with 4 things on the central atom, we can see if there's 4 things, it belongs to the tetrahedral family. So we can circle tetrahedral family. So I've got the tetrahedral family circled. Now it's time to find out what actual member of the tetrahedral family it is. Is it angular or bent? Here's the tetrahedral family right down here. Is it angular or bent? Is it trigonal or trigonal pyramidal? Is it tetrahedral? Well, how many bonded atoms were there? We had 2 bonded atoms. We had the 2 hydrogens right here, 1 and 2. So our B is 2. And we also had 2 lone pairs on the central atom. So our E is 2. It is the 2-2. It's the shape that goes with the 2-2. The 2-2 shape, B2, E2, is angular or bent. So we have the angular or bent molecule. I have angular or bent circled. I now can come down and finish the shape formula because it's AB2E2, so I'll fix the shape formula. Now this is in the tetrahedral family, so we've got the AB2E2 formula. What are the bond angles? Well, when we had 4 atoms, the bond angles were 109.5. When we replace one of the bonded atoms, maybe the one right here on top, the hydrogen atom, with a lone pair, that lone pair will push the atoms, there's the lone pair, that lone pair will push the atoms closer together than 109.5. It pulls them in about 2.5 degrees to 107. So now we're going to pull another atom off and replace it with a lone pair. A lone pair's left there, and now we have 2 lone pairs. One lone pair made at 107. Two lone pairs will push the atoms closer together still. It'll push them together to about a 104.5. 2.5 degrees closer again to a 104.5. When we look at our shape sheet, we're right here. Four things around the atom is tetrahedral family. We are in the bonded two atoms, B, two atoms for our E lone pairs. It was AB2E2. That's called angular or bent. Again, 104.5. This one will be asymmetrical. This one will be asymmetrical. Remember, for it to be symmetrical, it has to have all the same types of atoms. This molecule does. But the lone pairs, it cannot have any lone pairs to be symmetrical. So when we come out of our lone pairs of 2, E does not equal 0, so we're going up this way. It's not the 2, 3, or the 4, 2. The 2, 3 is linear. The 4, 2 is square planar. It's not the 2, 3, or the 4, 2. It's not one of our special molecules, so we continue on up. Our E is not equal to 0. It is asymmetrical. It is asymmetrical if there's different atoms surrounding the central atom. In this case, there's not. And or if our lone pairs are not equal to 0. They're not. This is asymmetrical. Our lone pairs are 2. So we'll circle the asymmetrical. Now, if it wasn't ionic, we would want to find out, is the molecule polar? If it's an asymmetrical shape, it needs to have polar bonds to be polar. Well, we know that this one would have polar bonds. Nitrogen's 3O, hydrogen's 2,1. The difference is 0.9. The electronegativity difference would be 0.9. 0.9 is greater than 0.4. Greater than or equal to 0.4. So we would come down here. We would circle the fact that it does have polar bonds, which would make it a polar molecule. However, we're not really worried that there's a dipole on the molecule because the molecule itself has a full charge. It is ionic. And that's really the strongest force we could have between two molecules is a full charge. So with that said, this takes care of our final problem on 6C8. If you have any questions that weren't answered in any of the videos, don't hesitate to ask.